Okay, so hello everyone. Welcome to another session of Your Clock. I am your host Akash Kundu, and I am a PhD student at Institute of Theoretical and Applied Informatics in Poland. And today, as a guest speaker, we have our own Gaurav Saxena, and he is a PhD student, fourth year PhD student at the University of Calgary. And he, during his PhD, he is not only working in quantum information and quantum algorithms and quantum optics stuff, like quantum resource theory stuff, but he is also ready to explore the philosophical aspects of it as well. And today, as you can see, that one of the interesting topics he's exploring in PhD is the topic of the talk, and he's going to give an introduction to quantum resource theories and its application to magic. So yeah, so thanks Gaurav for coming, and the stage is all yours. So please start.
Thank you, Akash, for inviting me to this coffee session. And I hope everyone who's here today gets something out of this talk. So let's get started. Let me close. And by the way, if you have any questions, you can, once I have covered the content of the slide, you can stop me and we can talk about it. So there is no need, like you can of course write in the chat, but sometimes chat disturbs the momentum. So you can either ask the question then, or once the slide is done, but there is no need, absolutely no need to wait to the end for the end of this talk. Okay, so as you can see, today I'll be speaking on the application of one of the applications of quantum resource theories, and that application is in magic. And I'm going to speak at a very introductory level. So if there are any questions, you can always ask me. And I'm assuming there are people from various backgrounds, and so I'll be starting with basics first. But just give me a second. Okay, so the outline of the talk is I'll first start with the very basic preliminaries that are required to understand this talk. Basically, I'll just be speaking about in the basic preliminaries about quantum states and channels. Then I'll talk about the general problems in quantum computing. Then we'll see how we can use magic as a resource to perform quantum computation. Then we'll see that once we enter this field, there are two divides in this field, and one is in the qubit case and the other is the multi-qubit case. So for the qubit case, we'll see how things are easily and neatly characterized by a representation called a Wigner representation. And in the multi-qubit case, which is actually the practically important case because everyone is trying to build a quantum computer using multi-qubits, there are a lot of problems when we characterize the elements here. Now, to do that, we take the help of resource theory, and this is when I'm going to introduce resource theories. Then once we have discussed what resource theories are, I'll combine both of these to give you the structure of the resource theory of multi-qubit magic. And then I'll be talking about some of my results. Basically, resource theory deals with interconversion among resources. So I'll talk about the interconversion tasks that I particularly solved in my recent work, one on qubit interconversion, the cost and distillation. Basically, my idea here is I don't want to discuss the technical details of my work. Rather, I just want to give you the definitions of what these terms mean, so that tomorrow when you see any resource theory talk, or when you read any resource theory paper or quantum information paper, then these terms don't scare you. And then lastly, this was my last result, classical simulation algorithm. But to be honest, I don't want to reach my results. They're kind of technical. So I just want to be at the more general introductory level. So yeah, let's see how it goes. So to begin with, let us start with the basics. And to understand any quantum information, we need to start by understanding how we represent quantum states and how they evolve. So quantum states are represented by density matrices, and their evolutions are modeled by quantum channels. So what are quantum states? Quantum states, basically, they are the states of a quantum system is represented by a square matrix. And this square matrix is known as the density matrix. So the density matrix is the most general representation of a quantum state. Any state, like it can be pure, mixed, classical, separable, entangled, it can be qubit, qubit, q-quad, q-quint, or any composition of different systems. Everything, any kind of physical state of a quantum system can be represented using the density matrix. In the community, it is usually denoted by rho, sigma, tau, etc. Now, what are the properties of this density matrix? So density matrix needs to be a positive semi-different matrix. That means it is a Hermitian matrix which has non-negative eigenvalues. So I believe everyone who's present in the audience right now, they understand what is the Hermitian matrix. Yes, no, because I think there are people like Niranjan and others. Any kind of thumbs up would work. Does everyone understand what a Hermitian matrix is? So I believe they do. Let's see in the chart. Hermitian self-adjoint, exactly. So they are matrices whose adjoint is equal to that matrix. So if I say if I have a matrix H, then H is equal to H dagger. Okay, perfect. Good. So any Hermitian matrix which has all non-negative eigenvalues is a positive semi-different matrix, and mathematically it is represented as rho greater than equal to 0. So this is the first property, and the second property is that the matrix rho, sigma, tau, whatever, it should have unit trace. So if I have a matrix which is positive semi-different and it has trace 1, then it is a density matrix. That means it represents the physical state of some quantum system, or any state of a quantum system can be represented using density matrices. So if I need to represent a ket, so this density matrix would be the matrix of rank 1. So I will stop here. If there are any questions, anything that anyone wants to clear or any doubt regarding quantum states, then you can talk about it now, else I'll move on.
Can you repeat the last statement that you made about rank?
Right. So if the rank of this matrix rho, this operator rho is 1, then it's a pure state. That means, so suppose I have a ket state, say psi. So psi basically is the density matrix, right? If I can very quickly use.
Okay, got it.
Yeah, got it. Okay, good. Just give me 1 second. I'll connect my tab. So if there is anything to write, I can. Okay. So moving on. So next things we want to see are how to evolve quantum states, and that is done using quantum channels. So they're also known as quantum operations or linear CPTP maps. So why we have these many names is because there are communities working in different types of fields. So for example, people who are working in quantum communication or quantum information, they like to call it quantum channel, because channel, it means that you're transferring some information from point A to point B. So quantum communication community or the quantum information community likes to call it quantum channels. Quantum computation people are mostly concerned by operations and how to, what I should act on a particular state so that it becomes another state. So that's why they call it quantum operations or gates if we are talking about the pure states. And otherwise, mathematically, it is known as linear CPTP maps. Sometimes people kill linear, as I've just killed linear. So it's usually CPTP maps. Otherwise, the full thing is linear CPTP maps. I think there is something in chat. Rose, right, exactly. So now, hold on. Yeah. So quantum channels, operations, or CPTP maps, whenever I'm going to use these terms in this talk, I'm going to use them interchangeably. And all of these quantum channel, basically, it models the evolution of quantum states. So this evolution can be due to noise, can be due to the presence of any unitary or non-unitary gate, or can be due to measurement or state preparation, any kind of process that you can think of in quantum mechanics is modeled by quantum channels. So quantum channels in general are the most general quantum state. So in the last slide, I told you that density matrix is the most general representation of a quantum state. Now I'm telling you that quantum channels is the most general way to represent anything. So by anything, I mean even quantum states can be represented by quantum channels. So suppose I have a quantum state rho. Now it can be seen as a preparation channel. That means if someone gives me a straight rho, I can say that, well, I have a channel that the moment I press one button, it outputs this straight rho. So any state can also be seen as a quantum channel, and therefore quantum channel is the most general quantum object in quantum information. So now what are its mathematical properties? So first of all, it has to be a linear map. I hope everyone understands what is linear. If I'll very quickly write it, just give me a minute. So just for completeness, I'm doing this. So where is my notate here? Good. So yeah, so any linear map is, suppose if I have a function f, it is called linear if it follows two properties. One, if I have a variable x, and if I multiply it by a constant lambda, then it is equal to lambda times f of x. So this is first property. And the second property is that if I have variables x and y, and if I say f of x plus y, then it should be f of x plus f of y. So if I have any function that follows these two properties, then this function is known as linear. Now, why do we need our quantum channels or operations or CPTB maps to be linear? So that they respect convexity. Okay, sorry, one second, let me erase this now. Okay, so what is convexity? So the thing is that because we can write any quantum state as a convex combination of two other any two quantum states. So whenever I act, so suppose this n is a quantum channel. So suppose when I act n on a quantum state, then it should give me a quantum state, and this particular rule needs to be followed. So this property is known as convexity, and because this has to be followed, this is a good physical requirement. Therefore, whatever description we are going to give to our n, it should be a linear map. The next property is completely positive. So completely positive mathematically just means that it takes a positive semi-definite operator. Remember, positive semi-definite operators are Hermitian matrices with non-negative eigenvalues. So it takes a positive semi-definite operator to a positive semi-definite operator. By operator, you can imagine it as a matrix. And even if the map acts on part of it. We don't need to go in a lot of mathematical details, just I'm giving it for, again, completeness purposes. And then the last thing is trace preserving. That means whatever this operation is, it should preserve the trace of the input and the output at the same time. So diagrammatically, it looks something like this, that if n is to be a quantum channel or a quantum operation, then it should take the set of all quantum states to quantum states. That means whenever you input any quantum state, even if the channel acts on part of the quantum states, the output should be a quantum state. So these are the three mathematical properties that a linear map, a map should follow in order to be called a quantum channel. So we can say it both ways. So if I have a quantum channel, then it has these three mathematical properties. And if some mathematical function has these three properties, then it is representing a quantum channel. So these were the basics that I just wanted to quickly cover before moving to the main part of my talk. So if anyone has any questions in quantum states or channels, I think this is the best time to ask. Wait for a very quick second.
Yeah, so why trace, it should be trace preserving? What is the physical significance of having trace preserving property?
Right. So, so the physical significance is that the quantum state should go to a quantum state, right? I mean, if so the trace of a quantum state is one. If you remember in quantum states, how we define quantum states is it is a positive semi-definite matrix with unit trace. So if the trace is not preserved, you're not giving me a quantum state. Of course, you cannot increase the trace, but if you're decreasing the trace, you're killing some information. You have done some measurement, and I don't know what you have. So to take quantum states to quantum states physically, the trace preserving condition and complete positivity, they both come from that point of view.
So in both the states, trace will be equal to 1, right?
Yeah. So quantum state. So if we go back to my previous slide very quick. So any quantum states mathematical representation is given by a density matrix, and the density matrix should be positive semi-definite. That means it should be Hermitian with non-negative eigenvalues, and its trace should be equal to 1.
Oh,
So any
okay.
quantum
Got it.
state is represented by this. So whether it is the input state or the output state, their trace has to be equal to 1, and therefore whatever linear map we are taking, it should preserve the trace. Does that make sense?
Yeah, totally. Got it.
Yeah, so I mean, correct me, Gaurav, if I'm wrong. Like this trace preserving comes from the concept of preservation of the probability, right? Because trace of a state is basically like the total probability, so it is 1.
Correct.
So if you apply a channel to that particular state, then there will be another state, but the total probability should be 1. It cannot just deviate from that, right?
Right. So quantum states are just a generalization of the classical probability states, right? So the probability is to be conserved. Yes.
Yeah.
One question over here. So
yeah,
you said that, of course, like we can represent a state in the channel formation, but then we are assuming that the preparations always starts from the all zero state, which is in like mathematically there's nothing like special about that. You can
no.
So when you represent a quantum state as a channel, as a state preparation like channel, then you assume it like it starts from the all zero state, and then that channel when applied on the all zero state gives you the state.
Technically no. So we just say that there is a trivial system. So by trivial I mean that there's a classical system connected to my state preparation channel. So this channel is something that whenever I press a Q on my keyboard, it gives me say row 1. Then when I press some other say W on my keyboard, it gives me row 2, and so on. So it is designed like when we talk about it like in this abstractions, we don't really go into the details. We just say that, well, you give me some trivial information and this channel is going to prepare a random state for you. So there is no need to give in just the zero state or anything else. We are saying that it is connected to some classical system. The moment you press one button, it gives you some particular output. Like it's just a preparation channel. That's all.
But the preparation channel depends on what input state you give to it, right? Otherwise, it won't be preparing the same state that you want.
So that's what I'm saying. So here, the input dependence is killed. So we are saying that it is connected to a classical system. So you give me some basic classical information. Okay. For example, you tell me you press the button X and some state row X get prepared.
Okay.
Yeah.
Just to follow up with Aritra's question. So like in the physical world, when we prepare quantum information, like we need to transmit some data. So how does that get prepared? So like in the real world scenario, there is no button like press Q and I will get the state. So how in the
right? So yeah, good question. So it's just an abstract model. We are just saying, so how people write it, I'll just quickly make it and then we'll discuss more. So the thing is, suppose this is a channel and it gives me some state rho X when you press some button X. Now how you can see it as suppose suppose let's take the example of Stern-Gerlach experiment. So suppose button say A gives you the state 0 and button B gives you the state 1. So the moment you press A, what will happen is I have a device which will pass some electrons through, and then there will be some zeros and ones, and it will block the ones. So whatever comes out are all the states in 0. Similarly, if you press the button B, then probably it blocks the 0 part, and whatever comes out are the 1 states. So something like that. Does that make sense?
Yeah, that makes sense. But to add on to this question, so if we want to prepare different many states in the real world,
Right.
So do we need to prepare apparatus like special apparatus for each of those states separately, like, or how in the real world man the क्योंकि the information is large, right?
Right. Right. Right.
There are not just two states. So how in the real world, like, I know it is like I'm argumenting over it, but I just want to get the feel, just the basic feel.
Right. See, so all I wanted to convey was that if I have a state rho, I can see it as a quantum channel. That's it. So if I have a state row, then it's some quantum channel. So maybe for every row here, you can think of in the abstract way that for every row, for every quantum state, there's a preparation channel. And suppose we have an infinite of them. So what? So if we can have infinite states, we can have infinite channels. What I'm trying to tell you here is that quantum states can be seen as quantum channels. And what are they? They are like the preparation channels. That's all. Now it might so happen that I have a very advanced preparation machine which has X and Y. There are 2 buttons, or there are 10 buttons, or there are 26 buttons, and then you can prepare 26 states. But in any sense, we can say that any state can just be seen as a preparation channel. So what, for some input, I can output this particular quantum channel, or quantum operation can output. So here is the classical input, and here is a quantum output. So there is no need for the input to be quantum. It's all quantum state eventually that is coming out.
Okay, got it.
So the only, again, I'm just repeating it again for the sake of clarity. The only idea that I'm trying to convey here is that any quantum operation, be it state preparation, be it any noise or any kind of evolution or any measurement, everything can be seen as a quantum channel. So quantum channels are the most general quantum objects in quantum information. That is the whole idea that I'm just trying to say. Now, how to realize it physically is another day's debate, but that is how we can look into it. Because see, what is the use of this? Like, why do I want you to see everything as a quantum channel? Because then we can capture everything in these 3 mathematical properties. So even the properties of of positive semi-definiteness and trace 1 can be captured using these 3 things. So it's all a part to mathematically put something in some framework, so that you can play around with that with only those properties, and you don't have to talk about different properties every time. That's the whole idea. Is that clear?
Yeah, that makes sense. Yeah, clear.
Okay. There is in chat, there is universal gate circus arbitrary can be used to decompose any quantum channels. Yeah.
No, that was an answer to Akash's question.
Yeah. Okay. Sorry. Okay. Good. So now let me move on to the main part of the talk, if everyone is okay with quantum states and channels now. So here is where my talk starts, and I need to just give me a second, clear my all drawings. Okay, good. So, okay. So as you all know, that we are living in a quantum era, and we always see, every now and then some news on quantum technology. Someone is building quantum computers, someone is, constructing quantum algorithms, someone is, working on quantum chemistry, quantum biology, and so on. So there is a lot of work in quantum technologies that is going on right now, and it's everywhere in the news. There are articles that are saying that, well, quantum computing is gaining momentum. IBM is saying that by 2030 we'll do this, we'll do that. INQ has made its stock public. It's kind of everywhere in the news. Investors, researchers, general public, everyone is interested. So there is a very big hype about it. But the truth is a little different from what it seems to be. And the truth is that we still do not have a perfect quantum computer. So whatever the goals the quantum computing community have right now, I think the main goal of the quantum computing community is to build a perfect quantum computer. Or if we say it in other words, it is to achieve universal fault-tolerant quantum computation. So what do I mean by a universal fault-tolerant quantum computers? So universal just means that whatever computer you built, you should have the ability to perform arbitrary quantum computation. That means any quantum computation that you can think of, any quantum algorithm, you should be able to run it on this perfect quantum computer. And by fault tolerant, I mean that if there are any errors that occur while the computation is going on, then those errors should be detected and they can be corrected, or at least their propagation can be brought under control. So if I have a computer which can perform any arbitrary quantum computation and I can control its error, then in principle, I have achieved perfect quantum computation. So universal quantum computation is achieved by a universal set of gates. So these universal set of gates are a finite set of gates. So this is like a small set of gates using which I can approximate any other quantum gate. And fault tolerant quantum computation is achieved by transversal gates. So transversal gates or a transversal architecture is a type of construction or an encoding using which if there is any error, then you basically detect it and correct it there. So it's a very nice architecture. Okay. So now going into more details of what is fault tolerant quantum computation. So fault tolerant quantum computation is usually in most of the schemes is done using stabilizer operations and states. I'll explain to you what stabilizer operations and state means in the next slides. But for now, just assume that there are a small set of operations and states, and using which we can control the propagation of errors in a circuit. But as you might imagine that because they're a small set, they cannot perform all quantum computation. So that means if you give me any quantum algorithm, these stabilizer operations and states would not be able to perform any kind of, or cannot approximate any quantum computation. So what do we do then? How do we go from a fault tolerant architecture to a universal quantum computation? And the answer to this lies in magic states and operations. So the idea is that you create a fault tolerant quantum circuit, and then you inject some magic states or put some magic operations in these stabilizer circuits, and then in principle you can perform or approximate any quantum computation. So that's where the role of magic states and operation comes in. So now let us understand what are stabilizer operations and states in more details. So stabilizer operations basically consist of three types of operations. One is preparation of quantum states in the computational basis. I'll explain to you what computational basis means. So one is preparation in the computational basis. The second is applying Clifford unitaries to evolve those quantum states, and then measurement in the computational basis only. So any quantum operation that can be written using these three is basically a stabilizer operation. So now let us see what is the computational basis. So computational basis basically is any basis state in which the qubit can exist physically. So for example, an atom can exist in ground state and excited state physically. So this particular state of the atom, or when you write the state of the atom as a linear superposition of its ground and the excited state, then we are saying that we are writing the state of the atom in its computational basis. Similarly, for electron, the electron spin up and spin down states are its computational basis. So if I am able to prepare any quantum state, and suppose if I'm able to prepare an atom in its ground state or in its excited state, then in principle, I'll say mathematically that I have prepared a qubit in its computational basis. Similarly, if I can measure in computational basis, then it is also an stabilizer operation. Okay. Now moving on to Clifford unitaries. So first of all, anyone has any questions up until now? Yes, no, I would believe in chat. Yeah. So but spin and down only in the z direction is computational basis, right? Yeah, exactly. So it depends. So in this case, it depends on the magnetic field that you've applied. Suppose you apply the magnetic field in the x direction, then the computational basis according to that scenario would be next, because x, y, and z don't really particularly have a real significance. It's just a direction. So it depends on in which direction you've applied the magnetic fields, and that would be your computational basis. Does that make sense, Rishi? Rishi? Also, Rishi, you can unmute yourself whenever, and that's what I told everyone, that if you just want to talk about anything, you can just
Hey
unmute
man,
and ask.
can you hear me?
Yeah, I can hear you. Yes.
Yeah. So okay, I see. I had previously thought only the Z basis was computational basis, but Z and X together cannot be a computational basis, right?
No.
I see.
You apply a magnetic field in a particular direction, right? And then depending on the direction of the magnetic field, you decide your computational basis in that particular scenario. That's particularly for electrons.
Interesting. Yeah. Thanks. That's super nice. Thanks.
Okay, great. So I hope the idea of computational basis is clear to everyone. To people who are listening it for the first time, you're going to hear computational basis a lot. So this is what it physically means. There is another thing in the chart. Okay, great. So, okay, good. Now let me move on. So now let us see what are Clifford unitaries. So first of all, I hope everyone knows what are unitaries, like unitary matrices or unitary gates. So they are mathematically saying it is just u dagger equal to u dagger u is equal to identity. So all of the logic gates are unitary. So these three gates are, I guess everyone must have seen them. So the C0 gate, that it takes, if it detects a 1 here, then it applies a NOT gate on the other qubit, the Hadamard gate, and the phase gate. So if I have any unitary that is composed out of the C0, Hadamard, and phase gate, then it's a Clifford unitary. So an example of a Clifford unitary would be the NOT gate. So, or the Z gate. So suppose if I apply the phase gate twice, then it in principle gives me the Z gate, right? Similarly, to achieve the X gate, I have to apply on 0, I need to apply the Hadamard first, and then I apply the phase gate twice, and then Hadamard. So any kind of combination of these three gates in any multi-qubit construction, or any construction, basically is known as the Clifford unitaries. So it's, as you can see, it's a very small set of operations. I mean, how many operations can you after all construct by applying these three gates? So the set of operations collectively is known as the stabilizer operations, and using these three operations, and of course all of their combinations and preparation and measurement in the computational basis, we in principle perform the fault tolerant quantum computation, or we detect and correct the errors. Now, the states that you can generate from stabilizer operations are known as the stabilizer states. So this is a very mathematical looking definition. Don't be scared. So I'll explain to you what this means. So conv means the convex combination of these states. So I'll come to that in a second. So what are these states? As you can see, if I act a unitary gate on 0, it gives me a pure state. So it is some psi. And it is not just some psi, it is all those psi that I can, all those states get vectors I can produce by applying the Clifford unitaries on 0. So Clifford unitaries are again any combination of C0, Hadamard, and the phase gate. So as you can notice, this is a rank 1 matrix and this is a pure state. So the convex combination means any probabilistic combination of these pure states. That means all of the probabilistic combination of these pure states are known as the stabilizer states. So they'll be the mixed stabilizer states. Now, let me give you an example for the qubit case. So suppose that this is the Bloch sphere, and this particular tetrahedron is the set of stabilizer states for the qubit case. So the extreme points or the vertices that you see here are the most popular states, like the 0 state, 1 state, plus, minus, plus I, and the minus I state. So all of these states can be formed by applying a Clifford unitary to 0. For example, to apply 1, I can apply just the NOT gate, and NOT gate is formed by applying Hadamard, then phase gate twice, and then Hadamard, and you will get the X gate. Similarly, I can produce plus and minus by applying Hadamard and phase respectively, and plus I and minus I. So these are the 6 pure states that you can generate by applying Clifford unitaries to the state 0. And all of their convex combinations are covered in this tetrahedron. So as you can see, it's a very nice geometry, even in the single qubit case. And as we go along in higher dimensions, it's a very nice convex polytope. That's how they call it, the convex polytope. If you don't know this word, then it's completely fine. Rishi, you have a question.
Yeah.
Yeah.
Thanks. So this is there a like simple to understand derivation why it's a hex? Why it's so regular and not a curved surface? Like why it's a plane and not a
good question. So the thing is that, I mean, this geometry automatically comes up from the Clifford unitaries that we have defined. So these Hadamard and phase gates, they only take it to, I mean, of course, there's a more group theoretic answer that I can give you, but maybe
no, I mean,
yeah.
No, I understand why it's the pure states, why it has to be only the 6 basis, the poly basis states. But I'm talking about the mixed states. So in the mixed state, it's like it's cut by a plane. And,
right.
And is it because this convex
combination? Yeah. So
yeah,
so
convex combination is linear
yeah.
in some sense, or?
Yes. So convex combination just means that suppose I take 2 states, suppose I take the state 0 and I take the plus. So first of all, I'm not taking the ket. I mean, it's a density matrix.
Mm-hmm.
So I'll just let me quickly write it down. Then it might be clearer. Annotate. Good. So suppose that I have the state 0, 0. All right. Can you see where I'm writing?
Yeah. Yeah.
Okay. And then suppose I have the state plus plus. There are 2 states and I take a linear convex combination. So convex combination just means a probabilistic combination of them. Okay. And I can also write, say something like say 0, like p1 times 0 plus p2 times say 1 1 and 1 minus p1 minus p2 times say plus plus. So this is also a convex combination. So any kind of probabilistic combination is known as the convex combination. Okay. So when I do this, so note that, say, okay, before going into this, suppose I have point A and if I have another point B, when I take a convex combination of A and B with respect to some origin, so all the points that I get are only in this line. So P times A plus 1 minus P times B is this whole line. So if I vary P from 0 to 1, I technically cover the set or all of the points on this line, right? So similarly,
I see your point. Yeah.
Right. So we technically have all the points here, we have all the points here, we have all the points here, and then when we take the convex combination here, we have all the so everything that is inside it is known as the convex combination, and this is mathematically known as the convex hull. So it is the shortest set of all the states that you can form from the convex combination of these points.
It's
just
mathematically called what?
Convex hull. Just to give you HULL, correct.
Okay, I heard hell.
no, it is actually a hell. So when we go to high dimension, this only becomes hell, and that's why things in qubit are very difficult. Anyway,
no, thanks.
Very one small doubt. So it's just the surface of the tetrahedron, right? Not the inside part.
Everything.
But then it won't be. Yeah, but only the surface, not the inside part.
No, everything. That's what I'm saying. So the whole tetrahedron, the solid tetrahedron inside. So even the identity, so the center of the block sphere is the identity. What is that? The mix.
Okay.
Yeah, that's also a Clifford unit. That's also a stabilizer state, not a Clifford unitary.
Okay.
Yeah. So all these states, because you see, so you can form all of them by. So if you suppose now you understand how we can form the surface. So I'm telling this for the sake of everyone, Aritra. So I hope everyone sees how we can form the surface of this tetrahedron by convex combination. Now, if you take a point on one surface and take a point on the other surface and take a convex combination, you reach the points inside this solid tetrahedron. So this whole solid tetrahedron gives me the set of states, and these set of states are known as the stabilizer states. Now, using these stabilizer states and stabilizer operations, the circuit that I form has the capability to detect and correct errors. So these are the states and operations that I used in fault tolerant circuits. Okay, so before moving on, anyone has any questions?
Yeah, one question.
Yeah.
So are these HC0 and S gate universal set of gates or not?
No, they're not. If they, so very good question. So suppose if they, let me write it down. So suppose H, C naught, and the phase gate, if they were universal, then we would, in principle, we should have the ability to reach any state, right? Because that's what operations do. If I input any states as 0, I should, by some of their combination, I should be able to reach any state rho. But look, I'm only able to reach this tetrahedron. I cannot reach a point here. I cannot reach a point here, right? Akash, does that make sense?
Yeah, that makes sense. Yeah.
Right. And so therefore, this set of operations, as you can see, as you can imagine, it's a very small set. Now, let me give you another example. So suppose if I write a matrix like this, 0 e raised to I pi by 4. So this state, this is this unitary gate cannot be reached by any combination of the Hadamard gate, the phase gate, or the C naught gate. It cannot. And so therefore, this set is far from universal, not at all universal. It's a very small set of operations that can only achieve some little things.
Is there a proof for that, Gaurav?
There is. It's a group theoretical proof. I'm not going into it today, but I can share you
just
the
asking.
details.
Yeah. No, thanks.
Yeah. No, don't be frightened if this is also abstract, both Arithra and yeah, exactly. So anyone, if you have any kind of basic doubt, please feel free to ask.
Okay, so this once can you repeat the point, like with any circuits which we create using stable states and operations, what is the special property regarding rectifying errors?
Could anyone else hear it? Or
I guess the question was like, what special property make this like tolerant to errors of the stabilizer states?
Very nice question. So the thing is, yeah, I mean, it's again, it has to be answered. This question needs a mathematical answer, but I'll skip to that. I'm coming to this. Why these stabilizer states and operations are important, and that is coming from this group theoretical structure. So it's okay if you have never heard of group theory, but the thing is that using math, we can show that the structure of these operations is such that you can trace them down very easily, and by measurements, by computational basis measurements, you can track what all is happening in those states. So, I mean, I can't give you a really nice example just by saying it out loud. Maybe I can refer to you an article later on, if that is okay, Niranjan. A very simple example, article. I hope that is fine. Okay. Assuming you're still there, and okay, yeah, okay, great. So now, why are we even bothered about stabilizer states and operations is what Niranjan asked, and that's where I quickly want to sum it up. That, as I've been saying, that these stabilizer states and operations, they're used in most of the fault-tolerant quantum computational schemes. Now, the thing is that it's good to have something that can, tolerate some errors. But what has been found out was that whatever computation that you can do using stabilizer states and operations can be simulated efficiently by a classical computer. And therefore, you do not get any quantum advantage. That means any operation, any kind of circuit that you design using stabilizer operations with stabilizer states as inputs, all of this operation, any kind of quantum algorithm that you design using these can be very efficiently simulated by a classical computer. And therefore, if I can do something by a classical computer, I don't really need to worry about using special kind of quantum gates. So it is good to know that they can perform fault-tolerant quantum computation, but they are technically useless because they do not give us any advantage in terms of quantum computation in achieving anything special with using these special operations and states. So what do we do then? How do we achieve universal quantum computation? Or by universal, I mean, how do we achieve any quantum computation? And that is where the role of magic comes in. If you remember previously, I showed you that the moment we inject a non-stabilizer state, these are the states which are known as the magic states in operation. So there is absolutely nothing special about magic states and operations. It's a good name, but they're only those states and operations which are non-stabilizer states, which do not fall under that category. Using them, we can think that maybe by using these magic states and operations, we can take our fault tolerant schemes to the universal quantum computation. So if you can see in this image, so there are these 6 block spheres. So suppose we take this block sphere, and this tetrahedron is the set of stabilizer states. Then the states outside this tetrahedron are my magic states or the non-stabilizer states. And maybe the question is, that's what 2004 people asked, that maybe we can use these states in the stabilizer circuits to achieve universal quantum computation. Okay, so now once we have realized what our resources are, there are many questions that arise, and some of them are these. So for example, if anyone gives you an arbitrary magic state, the question is how valuable it is. That means if someone, suppose if Rishi gives me one magic state and I am able to construct any stabilizer operation, stabilizer states, and I can do all the fancy fault tolerant quantum computation, can I perform any quantum computation by any magic state? So are all the magic states equally valuable, or are they not? Or are there some magic states or some non-stabilizer states which are actually of no value? And then how do I classify the states and operations that cannot provide me any quantum advantage? So I just found out that, well, the set of stabilizer states and operations are of no use to me in terms of quantum advantage. But then, are there some more magic states as well which cannot, which are technically useless? How do I know that? And then if you give me one magic state, then how can I convert it to any other magic state? So suppose I need a magic state B and I have a magic state A. Is the conversion always possible? Can I always convert magic state A to magic state B? So these are the questions that arise when you start thinking about magic as a resource for universal quantum computation. And to answer these questions, 2 branches have emerged. The first branch deals with the odd d-dimensional case. That means when we have systems like qubits or qquints. That means we have bosonic systems. We have 3-level systems. Like instead of 0 and 1, we have 0, 1, 2, 0, 1, 2, 3, 4. So these are the odd d-dimensional case. And the other is the multi-qubit case, the one which is the most popular case, which everybody keeps hearing about, qubits and all. So in both these fields, in both these branches, the answers are different. So the thing is that when we talk about d-dimensional states, suppose we are talking about qubits, then it is very easy to do this. Why is it easy? Because mathematically, there's a function, there's a representation called Wigner representation. Now, people who have done quantum optics definitely know what Wigner representation is. And if you have never taken a course in quantum optics, or if you don't know what a Wigner representation is, so it is just a way to characterize, to represent the the properties of the quantum state geometrically. So something like this. So I have a quantum state whose geometrical representation in the PQ, or the momentum and the phase space, is something like this. So just like, and now for people who have taken quantum optics course, so they know that the Wigner function is defined on an for infinite dimensional states. But even for finite dimensional states, you can construct a Wigner representation. So in this case, if you can see, it's like 1, 0, -1. So it's a discrete system, and still you can define a Wigner representation. I have something in the chat. What is on the z-axis? Z-axis is the intensity of the Wigner. So that's the value of the Wigner function. It is the probability. No, so when we take out the trace, when we basically integrate it, then it becomes the probability distribution. But in some sense, we can say that in some sense it is, as a whole, it's a quasi probability distribution. It's a distribution basically. So yeah. Now, so what do we do of this Wigner state? So let me give you a small picture here. So suppose this orange circle is the set of all these states and operations. The set of this blue circle represents the set of stabilizer states and operations, and I've made it very small because it is actually a very small set of operations. If you remember, stabilizer operations are only formed from the combination of Hadamard, C0, and the phase gate. Now, so if you remember one of my previous slides, one of the questions that I asked was, are there any states which are non-stabilizer and still useless to me when it comes to, to achieving universal quantum computation? And the answer lies for the odd d-dimensional case is here. So the states that that are in this green region, they all have a positive Wigner representation. So first of all of these stabilizer states, their Wigner representation is positive. So by positive, I mean the distribution is above zero all in all of P and Q. For these orange states and operations, there are certain areas. Suppose here there might be a small region which is below zero. So if this distribution is always above zero, then we call it we call that the state of the operation has a positive Wigner representation. Interestingly, it has been shown that if your state and operation has a positive Wigner representation, I can use a classical computer, I can use a traditional computer and do all the computation that you can do with these states and operations, and I can efficiently do it. So here we have a progress. Previously, we just saw that only the stabilizer states and operations can be classically simulated, but now there are more states, and there are states which are non-stabilizer states which can also be classically simulated. And so if they can be classically simulated, they do not give us the quantum advantage. Not just that, if I take any quantum state from this region and I try to use it, in the stabilizer operations to achieve any quantum computation, I cannot do that. So from these states, they're as useless as these stabilizer states, and I think even more useless because they cannot even provide the fault tolerant part. So this whole set of states, the ones in this green circle, are the states and operations using which we cannot perform universal quantum computation, and also they're classically simulatable efficiently, and therefore there is no quantum advantage from these states and operations which have a positive Wigner representation. So what about the states which do not have a positive Wigner representation? Now they become the prospective resources. So these magic states which have a negative Wigner representation, they are the prospect for achieving universal quantum computation. And this negativity naturally quantifies the magic. That means the more negative a magic state is, any non-stabilizer state is, the more valuable it is. So for the odd d-dimensional case, the Wigner representation is enough to characterize the elements that are useful and useless for universal quantum computation. So I'll stop for any questions. I know this is slowly getting heavy and I'm not reaching resource theory. I will reach it in a couple of slides, but any questions up until now for the odd d-dimensional case?
So sorry, yeah, go on.
Is there like any specific, can you interpret this geometrically where this more negative Wigner states, like representation states, lie on the block sphere, like for one dimension, for the qubit case?
Yeah, see again, as I'm right now talking about the odd d-dimensional. Yeah. I will come to the qubit part in a moment.
I understand. Yes.
Yeah, but to answer your curiosity, so the thing is that they are actually the pure states, and there are
like
special
kind of
types
farthest away or something like.
Sorry.
Like, is there some kind of like they're farthest away from the Clifford pure states or something?
Kind of, yes, we can say that. But then I cannot really say that because you see that's a qubit case, and for the qubit case, Wigner representation does not work. That's I was about to open this, but anyway. So that's why saying these things is a bit tricky. So in this case, when you say, to quantify how much valuable a magic state is, we just have to rely upon how much negative its Wigner representation is. But then when you say farthest, there are many things that come in my mind. So are you then comparing the trace distance, or are you just looking at it geometrically? So I think that connection has not been made, but I think that would be a good thing to study. Yeah.
Q intern projects. Okay, so so the question I had was Q-trig computations and qubit computations, they're equivalent, right? I mean, you can map one to another, can you not?
Sorry, say that again. So you're saying that qubit computations and qubit computations are equivalent.
I mean, so I thought they were, but now I'm asking if they are.
No, I mean, so of course you can in the mathematical sense you can map them by using isometry maps and all those things. Yes, you can do that. But when it comes to to this magic resource picture, they are not equal. And the phenomena that is responsible for this, I mean, see, Wigner representation is just a mathematical characterization, but when one can ask, like, what is the physical phenomena that is responsible, and the answer is contextuality. So it is actually contextuality that tells you the resourcefulness of the qubit case. But because for qubits, I don't know if many of you know this or not, for qubits, only the single qubit, like if I take a single qubit state, it is the only contextual state. For multi-qubit systems, contextuality does not hold.
What is contextuality?
Maybe another talk then. Let us not go into that.
No, sure. This is very interesting. Thanks.
Yeah. So it is so contextuality in very quick sense is a philosophical way of looking into measurements. It's like similar to non-locality, but how you see measurement observables given a particular context. But I know it is not clear by just making this statement. So maybe we can discuss contextuality later. I just introduced it just to tell you that yes, there is a physical phenomena also associated with the Wigner representation. So if you look at this picture here, so the states which are non-green states, they're actually contextual. So anyway, so not talking about this. It's the idea is that Wigner, let us stick with Wigner representation today. So any state which has a positive Wigner representation is useless. Yeah, so go on.
So one final question is it true to say that it only takes a polynomial amount of resources to convert a computation that is done in qubits onto qubits?
I'm not sure what that means.
So
you still want to preserve the fault tolerance or not?
Sorry?
You still want to preserve the fault tolerance or not?
I don't know. I mean, so I was thinking about your talk basically, Aritra, where you said the Church-Turing thesis equivalence, that different computational models are polynomially equivalent.
Yeah. So like that's the point. If you're not worried about the fault tolerance, then you can.
Then I can. I see.
But
so I'm not worried about fault tolerance. I'm only interested in magic state preservation, let's say.
Oh no, so we are talking about like perfect qubits, like there's no errors, and in that case you take any like qubit, you can like do the computation using qubit.
Oh, I see. So if it's a noisy mixed qubit, there's no
I mean, I don't know, like that part I don't know. Like for in the noiseless scenario, you can do all this, like using like polynomially extra operations.
Right.
Sorry, this is Anuj here. But I think in that case, the number of the qubits will be more, because the states which we are representing in case of qubits or qubits will be
yeah.
So it is
but they'll only be polynomially more. They won't be exponentially more. Yeah, they won't be exponential. They'll just be polynomial, like
or maybe even logarithmically.
Yeah, exactly. It will be logarithmically more. So that's what we meant when we said polynomially equivalent, and so on. But this is very interesting. Thanks. Please continue. Sorry.
No, good. This is something that I never thought of, but and good that this discussion happened. I'll probably look into it later on. Thank you. Thank you for this question.
Man. Oh no, but this is being recorded. This is very nice. Thanks.
Good. Okay. So so I hope I've convinced you all that for the odd, once again, why this cursor is not moving. Yeah. So I hope I've convinced you all that for the odd d-dimensional case, it is kind of easily characterizable to see which states are useful and which states are useless. And the answer lies in Wigner representation. So if your Wigner representation is positive in all of the phase space, then you cannot use that state or operation. For to achieve any arbitrary quantum computation.
Sorry, one final question.
Yes.
Wigner representation exists for mixed states also, or is it just
Yes,
for pure
it does.
states?
It does for all
Okay.
the states. Yeah.
Good.
Even for
Thanks.
quantum channels, for quantum operations, there is a Wigner representation. So if it's there for quantum channels, then it definitely holds for mixed states. Okay.
Thanks.
Okay, perfect. Good. So I hope it is now set in your minds that we can do things with odd d-dimensional states. But things are not quite right when we talk about multi-qubit systems. And why do we care about multi-qubit systems if things are good with the odd d-dimensional case? Because it is practically important. Most of the industries, all of the, everyone who's trying to build a quantum computer, they are trying to build a perfect qubit, and the operations that they're doing, the gates they're constructing, they're all multi-qubit systems. And therefore, we care about multi-qubit systems, even though we know that there is a very good mathematical theory that goes in the qubits. For multi-qubit systems, we are inclined because of its practical relevance. Maybe we are also inclined towards multi-qubit systems is because they're easier to control as compared to qubits, but that is just my guess. Maybe if someone has any comment on that, then probably they can add to it. Okay, so now the problem with the multi-qubit systems is that, like the qubit systems that we just saw, there is no function to properly classify the useless states or operations. There is no Wigner representation, no nice function or anything. So all the constructions have been very vague. So for example, I'll give you two examples. So there has been a function that has been constructed and used in a lot of places. But the thing is that that function takes only some useless states and operations. That means, first of all, the set of useless states and operations is already small. And then of that, also you have constructed a function that is small. So when we try to extend the Wigner functions from qubits to qubits, then this happens. So we are only left with only some useless states, and then there are some useless states that are left out. That means they technically become a resource. But we all know that we cannot use stabilizer states and operations for universal quantum computation, and therefore this particular function constructed in this manner is not good. Similarly, sometimes what happens is there are some researchers who have constructed functions, and their function included a larger set of operations than just the stabilizer states or operations or the useless ones. So in their functions, they also included some functions which are magic states, which are useful magic states. That means these states can actually be used to perform universal quantum computation, but in their scheme or in their function, they say that, well, this function, because it follows these properties, or this function satisfies this criteria, or this state satisfies this criteria, therefore this would be useless according to me. So that's what I mean when I say that there is no proper classification. That means if I construct a set of useless states, then that function should only contain the useless states. That means the states that cannot be used to achieve universal quantum computation. And that here is a difficult part, and this is an open question. If tomorrow any one of you solves this problem, I think that would be a very good paper. So this problem has been open for a very long time now. Okay, so now what the big question is, if we do not have a function to properly classify the useless states and operations, how do I quantify magic? So what do I mean by quantify? So because we have these magic states, which are a resource to achieve universal quantum computation, we want to find out what is the value of each of the magic states. Because if someone gives you a magic state tomorrow, then you should not just settle down saying, oh, that I've got a magic state and now I can achieve any quantum computation. No, you should ask how valuable it is, whether it is of any value or not. For example, in the qubit case, we just saw that there are some magic states which have a positive Wigner representation and therefore technically do not have any value. For the multi-qubit case, now the question is, because there is no function to properly classify the useless states and operations, quantifying the value of the magic states is a very difficult thing to do. And without quantification, people in theory do not move forward. Up until now, are there any questions?
One quick question is
Yes.
this. So, are all non-stabilizer states magic states,
Yes.
or only useful states are magic states?
All. So in 2004, I forgot the names of those two guys. One was Kurtzman and the other was, I don't know. So the other person, he wanted to become a magician in his life, but he became a quantum information theorist. So once he found out that, well, there are these non-stabilizer states that can be used to, achieve universal quantum computation, he said, well, let me fulfill my dream by calling these states as magic states, and let me become a magician. So that's
Right.
the story behind it.
It's
Yeah.
interesting. Yeah.
Yeah.
I see.
So
So non-stabilizer states are magic states. And
exactly,
then
all the non-stabilizer states.
only later we realized that some magic states are also useless.
Exactly. So I don't know if how many of you know about the bound entangled states. So it's the similar idea that there are only some entangled states from which you can distill the maximally entangled state.
Uh-huh.
So
Okay.
distill as in you use many copies of some state to convert it to one copy of, say, the maximally entangled state. But now the question is, can you use any entangled state to do it? And the answer is no. So the entangled states from which you cannot create the maximally entangled states are known as the bound entangled state. And the idea here is exactly same. So the thing is that, can we use any magic state to perform universal quantum computation? No.
Okay. Thanks.
Okay. So there's something in the chat. Okay, good.
I want to, I have some confusion about like this previous like D-dimension this system and this multi-qubit. So in the case of D-dimension, the Wigner function was able to distinguish between the stabilizer and useful and the magic states, right?
No, so Wigner function didn't discriminate between stabilizer and non-stabilizer. It just said that a Wigner function can only say that, okay, if a state is positive, you call it like it has a positive Wigner representation, and all the others, if they have any component which is less than 0, then it would be termed as a negative Wigner representation. It turns out that all these states which have a positive Wigner representation also contain the set of stabilizer states and operations.
Okay.
So it did not discriminate between stabilizer and non-stabilizer. We just found out that the stabilizer states and operations are a subset of the states and operations which have a positive Wigner representation.
Okay.
Right?
Yeah. So when you move to multi-qubit, then when you see the positive Wigner function, say, then there are many stabilizer states left out, right?
Exactly. So this green does not really contain the blue one. It might contain some of them, and it might leave out some of them. And there are some useful magic states which have a positive Wigner representation. So it's a complicated thing. So when we take the Wigner representation to the qubit case or the multi-qubit case, then mathematics there does not hold.
Okay, so I have like a very general question. So what is the value of D you need to choose? Where
D can be anything like 3, 5, 7, any odd prime D-dimensional states. And then when you form, so suppose you can take a qubit and a qquint and you form a system out of it, then Wigner representation will hold. But if you have a 4-dimensional system, or or which can again be seen as two qubits and so on, then the Wigner representation will not hold.
Okay, so it's like 4-dimensional state is multi-dimension, but 5 is odd 5-dimensional state, right?
It's not, I can have a quantum state which has 0, 1, 2, 3 states. Okay. Any computation that I do using these can be seen as the computation done by 2 qubits. Okay. See, if I take any number, say 15, I can factorize it as 3 and 5. So if I have a quantum state that has 15 dimensions, I can in principle do the computation by using a qubit and a qquint.
Right.
Okay. So that's what the idea. So that's why we don't really care about the systems with composite dimensions. We just say that, well, if for odd prime dimensions, this is the theory that holds, and any of their products. And that's why I'm saying odd D-dimensional states. But the moment any even number comes in, that means a qubit has to be involved. And for qubits, Wigner representation does not hold. So that's why I've clearly demarcated like all the odd D-dimensional states and the qubit states. because any other dimension can be broken down as a product of either the odd primes or the odd primes multiplied by the even, the qubit case. Right? So if you give me a number, say 22, then I can say it can be seen as a qubit like 2 multiplied by 11. But if you give me 21, then it's a 3 by 7. So I don't care about 21 because, well, for the mathematics behind 3 and 7 is very neatly given to me. But if you give me a 22-dimensional state, then I'll be worried because, you know, it involves a qubit. And the moment a qubit is involved, things, you know, just don't work well.
Okay, I got it. Yeah, thanks. It was very interesting.
Okay, so we have talked about this and now this. So what do we do? And that is where we use resource theory. So the question is, how do I quantify magic? Quantify means how do I find which state is valuable, which state is not valuable? And this is where resource theory comes to our advantage. So what is,
question?
yeah.
So like Wigner's function is like one way that people have explored, but are there also like different functions that people tried on like the 2 qubit or even
They
qubit
have
case?
a lot of functions have been tried. I mean, there have been a lot of functions written. There is one very successful function by Robert Rosendorf, and that was on rebits. So rebits are real qubits. So the qubits whose density matrices have only you know, real numbers. In that case, he wrote a function where he said that you know, the useless states or operations, not operations, he talked about states. So useless states can be characterized by this modified Wigner functions. But then the moment you know, but of course there are complex numbers in quantum mechanics. So the moment you have non-real density matrices, by non-real I mean they have like I in them, then his formulation doesn't work. So there have been a plethora of functions, plethora of papers in this regard. You can find it on, a lot of them are mostly in PRA, but because they do not properly do a classification. So
but that's also like a valid direction to look at, right? Instead of resource theories, you can also look at other functions.
It is no doubt. Yeah, it is. I mean, a lot of math has been done, but then again, see, the point is that if you do not properly classify, so if you have a theory, if you tell me that the left side of the block sphere is useless and the right side is useful, it doesn't make sense, right? I mean, I can say that all the functions which have a minus in them or something like that, they're useless to me. It doesn't make sense. So all these functions, they are a good research direction, no doubt. You can find some things, you can say some things about the experimental aspect of it, but it does not, you know, give me a good whole picture of it. It is still like only a part of it. So it's like giving a misinformation about something, right? Okay. So yeah, so and that's where we use resource theory. So before talking about how we can use resource theory in magic, now let me talk about resource theory. So people who are here to know about resource theory, you can now wake up. It's a good time. So the keyword in the resource theories is resource. What does a resource do? It helps us to achieve something that we cannot otherwise achieve. For example, if everyone right now is sitting in some space, in some, you know, in their offices, in their homes, or wherever. Now, in this particular setting in which you're sitting in, there are only a certain number of things that you can do. There are only some allowed operations. In your room, in your office, you cannot cook food. You can order food, but you cannot cook food, or you cannot, you know, play table tennis in your room. To play table tennis, you have to go somewhere. You have to spend your time and energy. You have to walk to there. So you have to spend some resource. So everything that right now is not in your room is essentially a resource for you. To do that, you have to spend something, either your energy, your time, your money, or whatever. You have to go out of that room. But in this room, whatever you have, you can access it freely, easily. And that is what is technically not resourceful to you at the moment in this given setting. So for resource theory, we need to identify the settings that we are sitting in, the constraints that are being imposed, and all the things that we can do in those settings. Okay, now let me move on slowly. I'll explain to you all these things in detail. let me take the example of the Marvel Comics universe. So the thing is that what I want to convey here is that resources are just everywhere, wherever you see them. So the Marvel Comics universe, the resources are the 6 Infinity Stones. Without these 6 Infinity Stones, we have Thanos, who is a very powerful villain. He can, is the capability to destroy planets and whatnot. But his aim of life, the goal that he has set for himself, is to create the balance in the universe. Without these 6 Infinity Stones, he alone cannot go to every planet creating the balance. It's just impossible. But the moment he gets these 6 Infinity Stones, with a snap, he creates the balance of the universe. So that is the value of a resource. The moment you get the resource, you can suddenly do something that you could otherwise not achieve. There's something in the chat. Interesting example. Thank you, Akash. So the thing is, what I want to convey here is that resources are just everywhere. You can always identify resources in any given setting. You first have to find out the constraints in that setting, what you want to do, and then what you cannot do is essentially a resource. Okay, good. Now, something in the chat. Okay, great. So now for a resource theory, what do we need to do? As I've been saying, we need to first identify the free or the allowed operations. So free is the term that is usually used in quantum resource theories, but the main term here is allowed operations. So how do you know what are your allowed operations? You first identify the constraints. You first find what is the physical setting you're setting in, and then given that setting, given the constraints, you see what you can do. And those are the things that we are going to call free or allowed, because they technically do not add value to your life right now. If you are hungry, you have to move out of your room, right? So given a setting, you have to find out what you can do, that those are the free operations. And from those free operations, there are some things that you can easily generate, and those will be the free elements. So for example, I don't know, suppose if someone is standing in the kitchen with the fridge and a stove, then in that setting, in the setting of the kitchen, food is not a resource. Food is the free thing for you, because you can take the raw vegetables, the allowed operation is cooking, and you can get a nice, or maybe not nice, food, but at least edible food. So that is something that you can generate easily, and that at that moment in that setting is not of any value to you. So identifying settings or identifying the constraints is the most important thing that you have to do in a resource theory. Once you do that, you know what are your allowed operations, and from those allowed operations, you know what are the things that you can generate. I hope this part is clear. And what you cannot generate easily, what you cannot do easily, is essentially a resource to you. If I give in that setting, if someone hands you anything else that you cannot do in that in the room, then now you have the capability to do something more. So everything else that you cannot do in that setting is a resource. So here is a very explanative and descriptive figure of a resource theory. So your allowed operations come from the restrictions. So that's why I'm saying it's a restricted set of allowed operations. You cannot do all the operations in this room wherever you're sitting in. You can only do some small set of operations which are restricted. From these restricted operations, there are some free elements, or there are some things that you can generate. So maybe you have a paper and pen, and maybe you can write a book here. So book is a free element of the product of your mind and you sitting in this room. And everything else is a resource. When we'll come to the quantum resource series, we'll see that the resources are of the types of, there are classical resources, there are quantum resources, noisy states or noiseless states, or noisy channels, noiseless channels. Static means there are some states, dynamic means channels. So all of these different types of resources are identified when you identify a particular setting. Before coming to quantum resource theory, let me dive more into into the resource theoretic framework. And before moving on, let me first say that sometimes what happens is that whenever we have a restricted set of allowed operations, we are not able to give it a good mathematical characterization. So let me give you an example. So maybe a lot of you know about LOCC, or local operations and classical communications. So that means there are, say, two experimenters. So suppose me and Aratro, and we both have our labs. We are doing some experiments and we can do any operation in our lab. But to create an entangled state in our lab, we cannot do it just by doing local operations and by classically communicating over video call or over a phone. So there has to be someone who gives us an entangled state, and then once we have the entangled state, we can do maybe some more things. So this setting is known as local operations and classical communications, or LOCC in short. Now, the thing is that characterizing LOCC is very difficult. No one has ever done it. If you do it, maybe it would be a great paper. So we understand what the settings are, but we cannot mathematically characterize it. So what do? What we do is we take the free elements and say that our allowed operations are the maximum set of operations that can convert free operations, or like the free states, to themselves. That means if I take a separable state, so from LOCC, local operations and classical communications, the state that you can generate is the separable state. Now, any operation that maps a separable state to a separable state is what I'm considering as free. Now I am breaking my shackles of LOCC, and I'm saying that any operation that takes a separable state to a separable state is a maximal set of allowed operation. So this set most of the times has a good mathematical characterization. By good, I mean it is comparatively easy compared to LOCC. But because it has a it has a mathematical characterization, I can work out things fairly easily as compared to LOCC. And that is why this set of operations becomes important. So here, the set of allowed operations is not coming from restrictions. Here, the set of allowed operations is coming from the free elements. You identify what the separable states are, and then you tell me what are the operations that are allowed. So, and that is why I drew both-sided arrow, because sometimes it is the operations that guide the free states. Sometimes they are the free elements guide the allowed operations. Does this make sense to everyone? Like, is the overall idea getting clear of what a resource, like what are the first things that we need to do in a resource theory?
Yeah.
So I want to just like clear something, because
Yeah.
it looks like the resource theory is basically like it needs a reference point, something like which kind of environment you are in, or something like that, what kind of
Precisely.
elements you are having, and
Yes.
while investigating that, you are actually creating a set of elements. This can be freely generated, and then you are taking something like exclusion set, which is basically like resources, right?
Absolutely correct. So the most important thing is to find the kind of setting you're in, either be it a quantum setting or in the real world. I'm coming to the real world example in very quickly. But overall, this abstract idea of how we go towards a resource theoretical approach, is it clearer? Like, does it make sense to other participants as well? Okay, I hope it is. Okay, there is something in the chat. Clear, great, thank you. So now, with this idea in mind of first of all, given a setting, we can go, given a setting, we know what are the allowed operations, and from those allowed operations, we know what are the things that we can generate, and those we will call free elements. But sometimes, because of strict restrictions, we have to define our free states first, and then define some certain set of allowed operations which can convert free elements to themselves. I'll come to these points in more details later on. But now let me give you an example from a real world. And in day-to-day, a very good example of a resource is money. You do not earn money for free. You have to work for it, right? So you do something, you spend some, maybe your time, you write a code for someone and they give you money. Now let us discuss it in a little more deeper detail. I'll keep this figure as a more descriptive example of resource theories. So suppose the allowed operation is farming. I have a farmer. India is an agriculture dominated country, a lot of farmers. And suppose there is a rice farmer. From his farm, what he can generate is freely is the rice, right? So allowed operation is farming. That's a restricted setting. He knows that in his particular state, there is a lot of rain and growing rice is the best thing he can do. So the allowed operation is farming, and especially say rice farming in this example. And what he can generate is rice. So now if someone, say suppose Akash goes to some village and he gives a rice farmer a bag of rice, he won't be very happy receiving that bag of rice. Even if you give him a different brand of rice, he won't be very happy. He'll be like, okay, I can produce rice. I don't want your rice as a gift. Maybe if Akash would have given him, say, a bag of wheat, he would have been happy, because now he don't have to spend some of his money to buy that some wheat. So for this rice farmer, everything in the world except rice is a resource. Does it make sense? But now the question is, yes, everything else is a resource, but if Akash is giving him a bag of wheat, can he exchange this bag of wheat in exchange? Like, can he exchange this with anything else? Can he go to to a retailer and buy anything with that? Maybe can he buy a bike by exchanging some multiple bags of wheat? And the answer is no. Then what is the resource that can allow him to do that? And that resource is money. So if he has money, then in principle, he can exchange money with anything. So anything except rice is a resource, but value-wise, money is the most valuable resource for him. And not just for him, for us as well. Money is the most prized commodity. If you have money, then what you can do, you can start a business. You can invest that money to gain more money, or you can exchange that money for any goods or services that you want. So in a particular setting, we identified what the allowed operation is. We identified what the free elements is. Then we know that everything else is a resource. But now we understand that everything is a resource, correct? But all of the resources don't have the same value. There are some resources which have only a small value. And there are some resources which have the maximal value. And in real life, we know that money is the resource with the maximal value. Does that make sense? So this is overall, this is the resource theoretic framework. And we can apply this resource theoretic framework in our day-to-day setting, or at least we can see in this manner. So once we have identified the resources, one may ask plethora of questions, and I'm listing some of the questions here just to ignite your curiosity. The first thing, as we just saw in the rice example, is the farmer may ask, if you give him a bag of wheat, what is the value of the resource? If it is not valuable, he is not really happy. But if you give him a resource which is very valuable, he'll be more happy. If you give him a diamond ring, he'll be very happy. Then the next question is, of course, as we were just discussing, that whatever resource I have, is it the most resource thing to have? And especially, is it unique? Like, is there only that thing in the world that is that much resourceful, or there are other things in the world? If you give someone 1,000 rupees, or if you give someone gold of 1,000 rupees, are they both equally resourceful? They're not. I mean, the gold's value might increase, your rupee might decrease, and whatever, all the scenarios, economic scenarios that happen. Then the next question is, if I have some resource A, can I exchange it with some other resource B? So for example, let us take this example from chemistry. So suppose I am Ukraine and I have some uranium with me. If you give me slow speed neutrons as a resource, which I maybe do not have, then I can give you the high speed neutrons. So I can convert slow speed neutrons to high speed neutrons. So I can convert one resource into another. And as you can see in the example, one slow speed neutron generates 3 high speed neutrons. So the question is, how many units of resource A I needed to convert to resource B? So for example, if I take 1 rupee as the element of the resource, then maybe I need 1 lakh of such coins, or 1 lakh rupees, to convert it to, say, a Tata Nano car. So the question is, how many units of resource A are needed to convert to resource B? And similarly, you can ask many questions once you have a resource. can you convert something probabilistically, approximately? And there are just plethora of questions that you can ask once you have identified the settings and the resources. So as we can see, that resource theoretic framework is a very general framework. It offers a unified approach to study various phenomena. Now, these phenomena I'll be talking about in quantum mechanics, so that's why I use the term phenomena, but it's a unified approach to study things. And let me make a remark that these resource theories are not new. They were actually used by people in economics to study micro and macroeconomics. And from there, we have borrowed the concept of resource theories to quantum. Anuj, you have unmuted. Do you have a question? Okay.
Sorry, I think it was by mistake. Sorry.
Okay, no problem. So then resource theories, they bring out great similarities at a deeper structural level. So at a resource level, this framework unifies all those things. We can look at a farmer and economics in the same way we are going to look at quantum mechanical phenomena. And then, because resource theory identifies resources for us, it tells us how we can compare the resourcefulness of different objects. How much valuable is one resource as compared to another. And because it is such a general framework, there are tools and techniques that I can use. Say in entanglement, the same tools and techniques can be used to study incoherence, to study magic, to study non-locality, and so on. So resource theory as a framework, it provides us with general tools and techniques. So that's a very good thing. Okay. Now coming to quantum resource theories. So quantum resource theories is very simply put, if whenever I see quantum mechanical phenomena as resources, then the resource theory that comes out of it is the quantum resource theory. So what do I mean by using quantum mechanical phenomena as resources? So if you remember the example I gave you, suppose Aritra and I have separate labs and we can do any quantum computation in our lab. But if Aritra wants to send me a quantum state through a quantum channel, which we do not have access to, then it is impossible. Because we can do local operations in our lab and we can classically communicate to each other. But we do not have the power to, to transfer a quantum information from one lab to another. Then what do I do? So if someone gives me an entangled state, and suppose someone gives me a maximally entangled state, then we can perform quantum teleportation. So quantum teleportation, what it does is, by some measurements and some preparation, Aritra can transfer some of his quantum information to my lab. And that's what is the communication of quantum information, which was previously prohibited. So in this setting of LOCC, entanglement is a resource. So entanglement is a quantum mechanical phenomena, but here we are using it as a resource to achieve something that we otherwise cannot achieve. Right? Does that make sense? Is it clear? Supposing it is, then we can see whole field of quantum information science as the study of interconversion among resources. Anything that you see in quantum information is just converting one resource to another. Anything at all. You're finding rates, you're finding capacities, bandwidth, anything at all in quantum information, whatever you're studying is essentially a conversion among resources. You're converting. How the question is, how can I convert one resource to another? What is the maximum number? What is the minimum number of doing this, that, and all that? All these questions come under the purview of interconversion of resources. And because I can see quantum information from this lens of interconversion of resources, therefore, there is no difference in quantum resource theories and quantum information science. They're exactly the same things in different words. When you view quantum information from a resource theoretic perspective, it just becomes quantum resource theories. So quantum resource theories is not, giving you anything extra. It's just a way of tackling the quantum information tasks. Now, for quantum resource theories, the free elements are ever free quantum states. The restricted operations are the free or the allowed operations. For example, in the entanglement case, as we have been seeing, the allowed operations are LOCC, and everything else is essentially a resource. I hope up until now, things are clear. If anyone has a question, you can ask right now.
Hi, yeah, Gaurav. So, in nutshell, like we consider teleportation as LOCC operation.
No, LOCC means what? It's a local operation and classical communication. Quantum teleportation is a quantum communication. You are taking one quantum information and technically transferring it to other side. So using classical communication, that means by telephonic call, if you have prepared a quantum state in your lab, you cannot transfer it to me. So quantum teleportation is a resource when LOCC is the setting. Does that make sense?
Yeah, because you cannot do teleportation. You cannot teleport the qubit when you have this local operations and classical communication, right? That's why it is the resource, right?
Exactly.
Yeah.
So in that setting only, if I'm only allowing local operations and classical communications, then the resource is an entangled state, and even the quantum teleportation is also a resource. But then the value of quantum teleportation as a resource is less than quantum entanglement, because it is the entangled state that allowed for quantum teleportation. So you see how resource interconversion leads us to the value of resources.
Hey, Gaurav, sorry to
Yeah.
interrupt, but maybe just for the YouTube video's sake, can we go through the presentation and leave the discussion towards the end?
Anything is fine. I mean, I'm fine with anything, but my idea was whether, I mean, if okay, up to you.
I mean, it depends. There are only a few participants here, so depending on what they have to say, would you like, if some people have to leave and so on, and maybe it's good to have like a short 1 hour YouTube video rather than.
What was the time?
Yeah.
Okay. Okay, we have gone beyond the. Okay. Okay, all right. So let me then quickly cover the quantum resource theoretic part. But before that, so Anush, did I answer your question?
I got it. So I was actually considering teleportation same as actually LOCC, but you clarified it as a resource actually.
Right. So you cannot do you cannot do quantum teleportation in the LOCC settings. Okay. So now moving on forward, because I think I'm running out of time. So one second. Yeah. So this is another defining figure that I'll be using in this talk. So the thing is that the free operations take the set of free elements to themselves. Everything else that is a resource, and the distance here basically tells me how valuable this particular resource is. And this function is known as the quantifier or the resource measure. So in resource theory of entanglement, we have covered here. So now, so this quantifier, now the thing is that resource theory helps us to compare the resourcefulness of different resources. So what are the properties of such a resource measure or this quantifier or this function? So whatever function I write to, to give this particular resource a value, what should its basic properties be? So the first property is faithfulness. Faithfulness only means that if I write down any function f of f, then its value should be 0 if and only if this row is a free state. For any non-free state, I'm attaching a number to it, and this should be a non-zero number, which tells me how valuable this is. Other way around, I can say that if I have a good resource measure and the value of f of row is 0, then I know that this row is a free element, because that's how I defined my row. And then the next thing is that if I apply any free operation on any resource, then the value of that resource cannot increase. It will only decrease, because see, it's free. So the quantum operation here, the n quantum channel is a free resource. It's a free operation. It cannot add value to anything, right? It can only decrease. Like how can you increase the value of something just by using the free or the allowed operations? And that is what is captured mathematically with monotonicity. We say that whatever state we get from n of rho, the value of that state n of rho will be less than whatever the value of n of rho would be, its value would be less than the original state f of rho. So if I write down any function which follows these two properties, then it is a resource measure. I can write a very bad resource measure for any quantum resource theory, and I can say that, well, f of rho is equal to 0 for all states, for all free elements, and f of rho is equal to 1 for any non-free state or non-free operation. It is a resource measure. 0 if and only if it is if it is free, and 1 if and only if it is non-free. But then the thing is this resource measure a good resource measure? Is it a good quantifier? Is it at all any helpful? No. So these two properties are the essential properties for any function to be called a resource measure or a resource quantifier, but they might not be sufficient, or they might not be good in the operational context, right? So this is what is the basic gist of quantum resource theories. I'll now quickly go on to the quantum resource theory at the level of quantum channels, because I told you in the starting that quantum channels are the most generic quantum objects, and because this is what I work, maybe I'll stop it at that point, and because I think that's we have exceeded by a lot of time here. So when we talk about quantum channels, when we talk about quantum resource theories at the level of channels, then the free elements are free quantum channels. The allowed operations are operations that evolve quantum channels. I'll tell you what how we can evolve quantum channels, and the resources are then all other quantum channels. Now note that, remember that all the quantum channels, when I say channels, they also include the set of states, because states can be seen as preparation channels. Therefore, this description, this quantum resource theory at the level of quantum channels, it basically covers all the aspects of quantum information. Now, very quickly moving on to the allowed operations. What do I mean by saying allowed operation? Evolving quantum channels. So suppose I have a channel N, and I do some pre-processing and post-processing in a way that there is some shared information E between them. Then we have technically converted the channel N to theta of N, where theta is this yellow portion, everything in here, and the pre-processing, the shared information, and the post-processing. So this object is known as a super channel. And when we apply theta on N, we have converted this N that took, say, system A0 to A1 to a system that takes something from B0 to B1. So this is how we evolve a channel, by doing some pre-processing or post-processing, or you can say by encoding and decoding. So in this case, the properties of a resource measure must apply for channels. That means the f of N is 0 if and only if the N, or the classical the channel is free. And monotonicity, that means if I have something that evolves quantum channels, the super channel, if it is free, then it cannot increase the value of N. And after that, I basically wanted to move to the resource theory of magic of multi-qubit operations, but I think it should be a good time to pause, because after this there are many technical results that I will be covering. So I think this is a good time to stop.
I will just stop the recording for now.
Yeah.